Hello all, welcome to the Basics.Academy. This is Smart Contract Security, Fundamentals and Auditing, a 5 units, 3 credit course in the BSc Blockchain Technology program. Let's get into it. In lecture 2, we are going to cover a few case studies in depth. We will specifically focus on the DAO hack, Ronin Bridge exploit, Wormhole incident, and the Poly network hack. The code examples shown in the further slides are simplified and illustrative. It captures the flow for teaching, not the exact production source. What we will dissect today: 4 hacks, 1 recurring lesson, read the flaw, then the fix. In case of DAO, the issue was Re-Entrancy Bug, wherein unsafe external call ordering happened. In case of Ronin Bridge, the access control and key custody failure led to the exploit of Ronin Bridge. In case of Wormhole, unverified signatures. And when it comes to Poly network, it was overprivileged executor plus the selector collision. What is the pattern here? The pattern here is almost every drain traces to a call that was made before a check or a check that was never made. Every hack happened either because of a call that was made before a check or a check that was never made. What is the re-entrancy mechanics? In case of re-entrancy, the withdraw function hands over the call to an external caller. From there, it goes to the attacker's fallback or receive function. From within the receive function, it again calls the withdraw function. So what happens? From withdraw, external call, from external call to the attacking contract, from the attacking contract again to the withdraw function, forming a loop. And this happens as long as the smart contract has ETH balances and as long as all the ETH balances is not being drained from the smart contract. So this is re-entrancy. Let us now look at the actual re-entrancy bug that led to the DAO hack. Here, if you notice in the withdraw function, first the external call is made, and after the external call, the state variable is updated. First, the external call is made, that is ETH is being transferred to the caller, that is message.sender, and then after the transfer, the state variable is updated. Watch the ordering. The money leaves the contract before the ledger says it did. From here, the money left the contract, and after the money has left the contract, then the ledger was updated. Now let us go ahead and have a look at the attacking contract. Here we have an attacker contract. So what it does, it has an attack function. From within the attack function, first it calls DAO.deposit. This is necessary to bypass the require statement check in the withdraw function. Whenever you are trying to withdraw, it will check whether your existing balance is greater than 0. To bypass that check, first the attacker contract deposits into the DAO contract. After depositing into the DAO contract, it calls DAO.withdraw. After calling DAO.withdraw, it starts the loop. In the next slide, we are going to see how exactly this happens. Receive and fallback, these functions run automatically on incoming ETH. Always treat them as attacker controlled entry points. Let us complete the entire cycle. What the attacker has done, first the attacker made a deposit to bypass the balances check. Then the attacker has called DAO.withdraw. So from here, the call comes to this function. From within this function, the external call is made, that is transferring ETH. When the external call is made, now in this case, message.sender is our attacker contract, right? So when the message.sender call happens, in reality, it comes to the smart contract's receive function. Now notice here, from within the receive function, it checks if the address of DAO contract is greater than 1 ether, keep on calling DAO.withdraw. So what it does, it again calls DAO.withdraw. So initially, the first call comes here, then external call. After the external call, it goes to the receive function. from within the receive function, again DAO.withdraw, from DAO.withdraw, again the withdraw function, and this loop goes on repeating. This loop goes on repeating. Why this happens? Because the state was updated after the external call and not before the external call. So this is the re-entrancy bug. The attack sequence, which I explained just now. First, deposit 1 ETH. Second, call withdraw once. Third, the DAO sends ETH, fires the attacker contract's receive function. Receive calls withdraw again. Balance still not zero. The check passes. The loop repeats, draining the pool. The whole hack is the order ETH. ETH leaves before the balance is zeroed. So, receive re-enters withdraw, while the books still say you are owed. If this line would have been written on top of the external call, there would have been no re-entrancy bug. So what is the fix for the DAO hack? The fix is checks, effects, interaction static. What happens in case of check? First, you run all the require and assert statements. Then in part of effects, you update the state variables that must be updated. And at last, you do the interaction or make the external call. Why this works? It updates states before any external call. You can also make use of OpenZeppelin's re-entrancy guards non-re-entrant modifier. So this modifier ensures if the external contract is trying to re-enter into your smart contract, and it will block the external caller from doing that. The whole hack disappears by moving one line up. Correct ordering is a security control. Let us now look into the Ronin Bridge hack. What exactly happened? In case of Ronin Bridge attack, the withdrawal always needed a majority of validators, wherein the threshold was set to 5 and there were total 9 validators. If you call the contract or call the withdraw function with 5 signatures, in that case the contract will proceed or will process your withdrawals. The important lesson in case of Ronin Bridge is a contract can be flawless and still be looted if the keys that authorize it are concentrated. So what exactly happened? Sky Mavis operated 4 of the 9 validator nodes itself. The hacker got access to his or her system, got away with the private keys. Once they had the set of private keys equal to the number of thresholds, they started calling the withdraw functions with appropriate signatures. So what they did, they signed their own withdrawals, which is approximately equal to $625 million, which was gone and it was unnoticed for approximately 6 days. So what are the defenses in such cases? Always decentralize the validators. Independent operators raise the threshold so no one party can reach it. Second thing is, make sure you have least privilege over time. That is, you revoke stale delegations and allow lists. Also, your permissions must expire. They should not be open-ended. Harden the key custody. Wherever the private keys are stored, make use of HSM hardware security modules or multi-party custody. Rotate the keys, say in 2 months or 3 months or in a single quarter. No single machine should be holding all the private keys. And at last, you can watch and throttle. You can impose withdrawal rate limits inside the smart contract such that if in case a hack happens, the hacker will get away with as minimum token as possible. Least privilege isn't just at deploy. The permissions you forget to remove are the ones that get exploited. The permissions you forget to remove are the ones that get exploited. The exact case has happened with the leash token, in which the previous developer has rebased the leash tokens n number of times which dropped the leash token price from $140 plus to less than $1. The lesson over here is least privilege isn't just at deploy. The permissions you forget to remove are the ones that get exploited. Let us now look at the wormhole incident. How the mint was forged. Step 1. It was locked on Ethereum, mint wrapped on Solana. Step 2. Each mint needs a guardian signed VAA. What is VAA? We are going to cover that in the next slide. The check read from an account the caller supplied. This is the most important step. The check read from an account which the caller supplied. It means the contract trusted the input data which the caller has supplied. In that case, the caller can be anything since blockchain code is open source. So the attacker got away with it. What the attacker did, the attacker passed a fake account with signature OK. They forged a VAA which helped them to mint 1,20,000 wrapped ETH, which was backed by nothing. So what happened? The code trusted an input that was supposed to be a proof, but the proof was attacker controlled, which helped the attacker to get away with 1,20,000 wrapped ETH. Let us move to the next slide and have a look at VAA. What is a VAA? Verifiable Action Approval. It is the signed message at the heart of Wormhole. It is a cross-chain message that Wormhole's guardians observe and cryptographically sign. The destination chain then performs an action, like minting a token, only if it carries a valid guardian signed verifiable action approval. So what happened? First, 100 ETH were locked on Ethereum. Step 1. 100 ETH were locked on Ethereum. Guardian signature, 19 guardians observe and give their attestation. In step 3, a verifiable action approval is emitted, which contains the message and the guardian signatures. And at last, in step 4, the signature is verified and the tokens are minted. If it is a valid verifiable action approval, then mint the wrapped token. What does a VAA payload contains? It contains a header, guardian set index and its version. It contains an array of signatures which has the guardian's signatures, and it contains the payload, the amount, token, recipient and chains. It is portable. Any chain can verify it independently. Why it mattered and how it led to the hack. The mint happens only if the VAA's signatures verify. Wormhole read that verified proof from a caller supplied account. This is the important point. Wormhole read that verified proof from a caller supplied account. The caller supplied account in this case was the attacker. The attacker has given a forged VAA that led to the Wormhole contract to believe that the VAA was valid. In turn, that led to minting of 1,20,000 wrapped ETH, which were backed by nothing. So the attacker faked it. The attacker forged a verifiable action approval, then minted 120,000 wrapped ETH, which approximately equals to $320 million. And these tokens were backed by nothing. So what is the fix? Verify the account is genuine. Load instruction add checked. What is the load instruction add checked? We'll look at in the next slide. In common terminologies, think of verifiable action approval as a signed permission slip. Forge the signature check and you forge permission to mint. What was the fix in case of Wormhole? Verify the account is genuine before you trust what it says. In the previous slide, this argument was given by the caller, but the fix says the checked variant rejects any account that isn't the genuine system account, and Solana's official system account that lists a transaction's instructions by checking sysvar instructions. So this is Solana's system instruction. If Wormhole would have used this system variable instruction instead of the caller supplied variable, the Wormhole hack would have never happened. The safe variant validates the account address. The forged account is rejected and the fake VAA never meets. So what are the lessons from Wormhole incident? First is never trust caller supplied accounts or inputs as proof. Always validate them. Never trust caller supplied accounts or inputs as proof. Always validate them. This is the most important lesson when it comes to smart contract development or auditing. At last, let us look at the poly network hack. We are going to directly jump to the next slide because the next slide explains the entire attack vector in a visual format which is easier to understand. However, I want you to take into consideration only this line. What it says, it can call any contract or any method. To.call, ABI.encode pact, the signature and the arguments. Now these arguments are being passed down from within the function. Let us go to the next slide. What exactly happened in case of, say, poly network hack? What the attacker did, the attacker crafted a cross-chain message that had arbitrary data, arbitrary target and data. The ETH cross-chain manager contract, it called this function execute cross-chain transaction, which internally called to.call with signature and arguments. Coming to the next part, what happened? ETH cross-chain data. Have a look at here. Selector collision. This is the function put current epoch con pub key bytes. This function can only be invoked by the owner of the contract and the owner of the function. The owner of this function is equal to the ETH cross-chain manager contract itself. So if you are able to, from within this line, if you are able to invoke this function, passing in arguments as your controlled wallet addresses, so what it will do, it will update the owners by calling this function. Not the owners, it will update the keepers by calling this function. That exactly happened in this case. What is the only owner modifier? It checks that the caller is the owner which has been set in the smart contract storage. So this function put current epoch con pub key bytes is only owner. What happened? Owner is manager and message.sender is manager, right? Because from within this contract, the attacker created arbitrary target and data wherein this signature was that of this function signature and the arguments it accepted was that of what argument this function accepted. This modifier was bypassed because this function was being called from within the same contract, due to which the message.sender equal to owner check passed. The caller is the owner, only owner passed by default. Once this was done, the attacker replaced all the keepers. The attacker's key becomes the trusted signer. Then the attacker forged withdrawals, that is, it signed its own transfers, and by doing so, they drained approximately 600 $10 million from the Poly network contract. Nearly all were returned later, and that hacker in the crypto community is known as the white hacker. What is the fix for such cases? Whitelist call targets. This one, 2.call. These are call targets. So you should whitelist call targets and selectors and separate privilege. In this case, the ETH cross-chain manager contract had multiple privileges. It was able to call its own function, and it was also the owner, right? So what it does, from within the contract, this function was invoked, due to which the message.sender was nothing but the owner itself. The only owner check was bypassed. Doing that, the hacker replaced all the keepers, forced withdrawals, and drained $610 million. So the lesson is whitelist call targets and selectors and separate privilege. A generic executor must never be able to reach an admin function. In our case, or in case of the Poly network ETH cross-chain manager contract, this is a generic executor. It can call any contract with any data. So a generic executor must never be able to reach an admin function. Out of these 4 hacks, we learn one simple lesson. Read the root cause, then the principle it violated. In case of DAO, the root cause was unsafe external call ordering that led to re-entrancy. What is the fix for the DAO or the re-entrancy hack? It is check effects interaction pattern. In case of Ronin Bridge, the root cause was concentrated trust and stale key delegation. What is the fixed principle? Least privilege and decentralize the validators as much as possible. In case of Wormhole, you should validate every input and not trust them as it is. In case of Poly network, the privilege must be separated. That is, if the ETH root chain manager contract would have not been the owner, in that case, the Poly network hack would have never happened. None were toxic. Each is a named teachable pattern, which is exactly why auditing works. A secure coding checklist from these hacks. It is advised you should carry this into every contract review and into the lab. First is order state before calls. Always apply checks, effects, interactions pattern, and make use of OpenZeppelin's Re-Entrancy Guard smart contract. Second is lock down every function. Restrict sensitive functions with rules or only owner, and make sure that you have separate privileges. Whitelist call targets. Never let a generic executor call arbitrary contracts or selectors. That is, in case of Poly network, the 2 call, in case of 2, those 2 must have been whitelisted. When we say whitelist, we know what the contract is and what code that contract is going to execute. Fourth, you should always verify all the inputs that is coming into the smart contract. You should not trust the caller or the attacker. Fifth is management of keys. Make sure if your smart contract has a huge amount of funds into it, the keys which have access to the sensitive functions or are the admins or the owners, those keys must be stored in hardware secure modules. Those keys must be rotated, say monthly or quarterly. If you are using multi-signature wallets, make sure you have high thresholds and all the owners are at different geographical locations. And make sure that whenever you are granting access to any private key or any wallet address, that access must be time-based, it must expire. Last but not the least, you should monitor and be able to pause. One tip, make sure to inherit your contract from OpenZeppelin's pausable contract. In that case, whichever function has A ETH transfer call or any token transfer call had a modifier when not paused. So if at all a hack happens, you can submit a transaction, pause the contract, and stop the hack midway. Most audit findings are one of these 6 lines which were unchecked by the developers. Last but not the least, what are the key takeaways from lecture 2? The fix is usually small. Reordering a line, one check, one modifier, not heroic engineering. Not every hack is a code bug. In case of Ronin, the private keys were compromised and Solidity did what it should do, and it did exactly that. Trust nothing from the caller. Be it inputs, accounts, or signatures, these are all attacker controlled until verified. You should always verify the inputs. What we are going to do in the lab part, we are going to reproduce the re-entrancy attack and access control flaws. Going ahead in the next section in Unit 2, we will cover secure Solidity functions. That wraps up this session. If it helped, like and subscribe so you don't miss the next one. Questions? Drop them in the comments below. See you in the next lecture.